Here, we're going to talk about matrix inversion, computing the inverse of a matrix, and solving simultaneous equations are related tasks. Basically, matrix inversion is an application of simultaneous equation. So look at this equation. AX is equal to an identity matrix. When you say identity matrix, the diagonals are 1. Okay, where I is an identity matrix corresponding to the variable b in original simultaneous equation. AX is equal to b. The solution x is simply the inverse of a. Okay, by looking at this equation, so if you transpose a to the other side, making it with a inverse of a, okay, then x, you will get the variable x. Okay. We know that a is the coefficient matrix of the system of simultaneous equation. Okay, so here is the formula for the inversion. So you will see that we simply substitute b with identity matrix. Okay, so we have here an a and b. So this is a NumPy library. So given the length of matrix A, then you can create an identity matrix. So we can show this by giving an example. Oh, sorry. Okay, so assuming that we have a we can try this example. Okay, and see what is the A inverse. Okay, so we can delete this one. Oops. Only integer. Okay, so sorry, I forgot that we need to get the length, or maybe directly get the length of A. Oops. Okay, so you see the diagonal of matrix identity matrix is 1, and then the rest is 0 or sparse. We call it sparse. Okay, so we have this identity matrix. So yeah, that's the case. Now so we have a user-defined function math inverse, and you see we are using LU decomposition, and then to solve to get the A inverse. As I said earlier, I is simply the b variable b, and we substitute b with the inverse, or sorry, the identity matrix. Okay, so this is the function. So let's try an example. So given the same example a while ago, okay, so this is the A. Okay, and then you know that the identity so this one is the same as before. So 3 by 3 with the diagonal elements in equal to 1, and then the rest is 0. Okay, so we have here, so we copy first A. Okay, we copy so that we can save the original A. We don't use A. Okay, and then we can inverse A inverse. Then we math inverse, okay, A. So this is the function we have defined earlier. So simply we use the LU decomposition, LU solve. So if you haven't if you would like to understand these two functions, so I'd like you to watch the previous video of this. Okay, so let's proceed. Okay, so we haven't defined yet. Okay, so we can run the code LU decomp from the previous one, then the other one. Okay, so those are the two functions. So then this will work. Opo, I also the swap rows. Sorry for that. I restarted this okay, here you go, swap rows. Okay, and going back to that example, so we have here, so you see we have tried to troubleshoot problems. So if you encounter a similar problem, so you just simply go back to the previous user-defined functions and try to run them again. Okay, so this is the inverse of sorry, So this is the A inverse. Okay, this is the result of the function mat inverse. Now, if you multiply A inverse with the original one, so making this A times A inverse, then the answer should be an identity matrix. If you notice, the answer is very small, close to 0. Okay, this is close to 0, these values. The question might be, why, how come this one is not 0? It's because of the truncation error. Okay, so because of the, for example, this one is a repeating number, so it should be 5 5 5 5 5 5. Okay, so if you multiply with the A inverse, it's not completely equal to 0. Okay, so but it's very small. That is, we can remove the significant figures and then round it off, it becomes 0. Okay, so basically we got the correct inverse. Okay, so this is the inverse. So if you multiply the inverse of A with itself A, then the answer would be identity matrix. Okay, so something like this. um, so if you multiply A with A inverse is equal to identity matrix. Very, very simple. Okay, any matrix A. So we know that A matrix, I matrix or identity matrix is 1 0 0 0 1 0 0 0 1. If matrix A is 3 by 3. So if it is 4 by 4, then also the matrix will change, no, accordingly. Alright. So when the matrix is tri-diagonal, we use LUDCOM3 function in matrix inversion. So we can also use this one, no? If tri-diagonal. So what do you mean by tri-diagonal? So you see here a you have the diagonal, so the primary diagonal, and then you have the secondary, two secondaries, just beside, adjacent to the main diagonal. Okay, so that's why we call this tri-diagonal, but this is seldom happen. Okay, this is not common, so but this is just an example. Okay, so given that so these are the three functions. Basically this is the same as LUDComp and LUDSolve, but in the three there's another three here, okay, compared to the previous one where there's no three. So we defined a new LUDComp. Then let's try now. One thing um, we need to remember how to get A. So A, you can make a matrix like this. So you create this one, no? So but you can do it manually, like you manually put 2 -1 0 0 0 and then negative, so no problem. But if you would like to make it faster, you can also do like this, no? So once is simply how you call this, once, so it's a matrix creation wherein I think this one inside is the shape. Okay, n is the diagonal, so you count the number n, 6, so this is 1 2 3 4 5 6. Okay, so all the 6 elements there, once multiplied by 2. Okay, so that's 1. So once means a matrix with 1. Okay, only the diagonal values, and then multiply by 2, so then it becomes 2. But there's 5 here. Okay, later. So if there's, so the matrix here, n minus 5, so he assigned 5 instead of 2, he assigned 5. Okay, and then E, n minus 1, so it becomes -1. Okay, so -1. And then copy. Okay, C, I try to copy the other side. Okay, oh, all right. So then you have then creating A inverse with the same diagonal, the same matrix size. So this is 6 by 6. So n is equal to 6. So then we can create a 6 by 6 matrix with only the diagonal equals to 1, and then the rest is 0. Okay, and then using the function LUDComp3, similar to LUDComp, but focusing mainly on the diagonals. because here, so they stop calculating the other side because obviously the rest are 0, so you can actually create your own, no, ignoring the zeros. Okay, if you have a system with a lot of zeros, okay, so you can ignore them so that you can save time. Okay, you can save your computer um, power. Okay, in this case. Okay, so then we can run this one. So one, so you can see we can actually view the inverse for you to check. Okay, very good. And then we can as well see the D. Okay, so that's a diagonal. And then we have the E. This is all -1, and then the C. Okay, now here, so it plug in KCDE, the one we have just displayed, and then it will be used here. Okay, and um, then the result of this one becomes return CDE. So let's see what will be the result of this, and actually we can. Okay, so array. So it's just simply making array, and then solve with the A inverse, and then you have your inverse matrix. Okay, so the inverse of this matrix is simply this one. Okay, the values here, you can see here. Okay, CDE from the LUD comp. So here, it's just simply allow us to make a modification in the matrix. Okay, so then yeah, so the solve, the LU solve. So we know the decomposition, it's like the forward, the forward computation. Okay, if you can remember the previous one for the LU decomp. Okay, and then we have the LU solve for the backward um, backward solution. Okay, so then we will get the A inverse. Okay, so this is the A inverse. Now this is only for tridiagonal matrix. Okay, so that's it. Pretty simple. What really important here is the inverse. So knowing that matrix inversion is an application of simultaneous equation. So linear simultaneous equation. So um, it's very important, and just to make sure that you understand this thing in your engineering math, and then we have just applied that one. Okay, so this is the main and very important application of the linear simultaneous equation, and later on we will discuss more about these applications. Okay, and then our next topic will be iterative methods. Thank you for watching.